Okay. Second order linear differential equations. Let's continue. This is the third lecture. So I discussed this homogeneous equation, and I found this AR squared BR plus C equal to 0 characteristic equation. And solving this will give us three cases. Case 1. Case 1. So case 1 is two distinct real solutions, R1, R2. So Y complementary is C1 E R1T plus C2 E R2T. 2 is two complex solutions of the form alpha plus minus beta I, and here beta is not 0, alpha can be 0, and that gives me a yc is e to power alpha t, c1 cosine beta t plus c2 sine beta t. And the third one was one solution with multiplicity 2. Say the solution is R. So let's say it's R, so Y complementary will be C1 e to power RT, C2T e to power RT. So let me give you 3 examples of each, and then I will discuss the particular solution. Okay? So these are the 3 cases that I discussed last time. Okay. Examples. Example 1 and 2 real distinct solutions. So it's y double prime say plus 5 y prime plus 6y equal to 0. Let's assume that y at 0 is 1 and y prime at 0 is -3. So I am giving you initial conditions. So characteristic equation is r squared plus 5r plus 6, 0, and that is in fact r plus 2 times r plus 3 is 0. So I have r1 is -2 and r2 is -3. So the complementary solution will be c1 e to power minus 2t plus c2 e to power minus 3t. Now I have to apply the initial conditions. One of them is y at 0, the other one is y prime. So I need y prime. Y prime c is minus 2 c1 minus 2t minus 3 c2 e minus 3t. Okay, so now applying the initial condition, that gives me y at 0 is 1, 0 will give me 1, 1, so it is c1 plus c2 is 1. The second one will give me, this is 1, this is 1, so I have minus 2 c1 minus 3 c2, it is minus 3. Okay. Well, this is just 2 equations with 2 unknowns, just solve it any way you like. I would multiply this by 2 and add to this. So if I multiply this by 2, I will get, let me write it here. So I have 2 c1 plus 2 c2 is 2, and this is minus 2 c1 minus 3 c2 is minus 3. So adding them 0, that's minus c2 is minus 1, so c2 put C2 here in the first equation, C2 minus 1, C1 minus 1 is 1, so C1 is 2. Okay, so the solution, the y particular will be, let me write it here, yp will be C1 2 e to power minus 2t minus 1 e to power minus 3t. So that's the particular solution. Let me double check. 2 and 3, that's correct. Minus 3. Okay, then derivative is minus 2, minus 3, and C1 and minus 3. So multiply that. I have minus 1 here, minus C. Oh, C1 is 1. Plus 1. Right. So this is plus 1. It's good to check so you haven't made any mistakes. Okay, so that is example for case 1 when we have two real distinct solutions. Solutions for this characteristic equations. Well, let's write the roots here. So roots A. Okay. So example 2. This. Example 2 is two complex roots. Roots. Y double prime, plus 2, y prime plus 2, y is 0. Let's say that y at 0 is 2 and y prime at 0 is negative. Okay. Initial conditions. So the characteristic equation is r squared plus 2r plus 2 is 0. So I have r is minus 1 plus minus square root of 1 minus 2. So this is in fact minus 1 plus minus 1. Okay. So let me double check. Minus 1. Okay, correct. So what is alpha and what is beta? Alpha is in fact negative 1 in our case, and beta is 1. Okay. So the complementary solution, the general form will be e to power minus t. This is 1 here times c1 cosine beta is 1, so it is cosine t plus c2 sine t. And I need y prime, so let's write y prime c. There is this one times this one, which is minus e minus t times c1 cosine t plus c2 sine t, plus there is this one times this one, plus e to power minus t. And then there is the inside will be, the first one is minus c1 sine t. This is cosine plus c2 cosine t. Okay. Now, one of the common mistakes that students make is, in fact, that when it comes to finding the derivative, they just make a mistake. Remember, the product rule is fg. The derivative of fg is f prime g plus fg prime. Okay, so be careful. It's not f prime g prime. Okay. So, well, let me erase this middle part. Because I need this, and I need those two. So let me draw some lines here, and it's apply the initial conditions. Y at 0 is 2, so this one will be e to the power 0 is 1, so cosine 0 is 1, sine 0 is 0. So this one will be simply c1 times 1, c2 times 0, everything times 1. So this is, well, first one gives me c1. Now the second one, y prime at 0, so I will get 1 here, 1 here, 1 here, 0 here, 0 here, 1 here. So I have a 1 times c1, which is 2 here, then plus 1, and this is in fact minus, right, minus 1, plus 1 times this will be 0, and c2, and this is negative 1. Okay, so this one is in fact minus 2 plus c2 is negative 1, so c2 is also 1. Right, so the complementary solution will be e to the power minus t times c1, c1 is 2 cosine t, and c2 is 1 plus sine t. Okay, let me double check. So that is in fact minus 1 plus minus 1 minus 2, that's minus I, and that's correct. And derivative will be minus this times minus c sine plus c2 cosine, and applying this will give me minus 1 times 2. This was 2 here, c1 is 2, then 1, c2. And c2 minus 2 is minus 1, so c2 is 2 minus 1, which is 1. Okay. You can check my calculations and correct if I have made any mistakes. So that was the second one, the second case in fact. The third case is when we have one root. One root with multiplicity 2. So let's just go with the simplest one. Y double prime, okay, so plus 6, y prime plus 9, y is 0. So I have r squared plus 6r plus 9 is 0, and that is r plus 3 squared is 0. So r is minus 3. Well, let's assume some initial conditions here. So let's assume that y at 0 is say 5, say, and y prime at 0 is negative 1, something like that. So just something. Okay, so this gives me y complementary as c1 e to the power minus 3t plus c2t e to the power minus 3t. Now, it might be better to write it like this, so when we find the derivative, because I need the derivative of this, it might be easier to write. So both of them have e to the power minus 3t, so I can write it as c1 plus c2t. Okay, now I need the y prime. So y prime, c will be this one times this one minus 3 e to the power minus 3t times c1 plus c2t. And there you go. This one times this one is simply just c2. So e to the power minus 3t times c2. Okay. Now applying initial conditions, y at 0, e to the power 0 is 1, so that gives me simply c1 is 5. y prime at 0, this will be minus 3 times c1, which is 5, and this is 0, plus 1 times c2, and that is negative 1. Okay. So this is minus 15 plus c2 is negative 1, so c2 is 14. Okay, so y p will be e to power minus 3t times c1 of 5 plus 14. Okay. So that was again, 3 examples for each case. That's how you do it. Now, when we are given a differential equation with the right-hand side 0, homogeneous case, if you are not given initial condition, or let's say if the initial condition is 0, 0, 0, then whatever that equation is modeling, that system is not really moving. So let me give you an example of the system and tell you what this y0 and y prime 0 are in fact. So the practical practical example is this. So from vibrations. Let's say that we have a spring, mass, and damper system. So this is spring, mass, damper system. This is M. And there is a damper here too. So okay. So this is moving left and right. Suppose it's moving this way, so let's say that this is in fact positive, and it is x. And let's say dx dt, in physics they put dot here rather than prime. So if I draw the free body diagram, then if it's moving this way, then these two oppose. So I have a force here, this is K and this is C. This is Kx, and this one C is in fact the force comes from speed. So if it's moving without too much velocity, then the force of that damping is small. But if it's moving with enough velocity or larger velocity, then the force is larger. It's like a seat belt that if you pull it slowly, it just goes like that. But if you pull it hard, boom, it stops, something like that. But it's not that, but anyway. So if you push the damper slowly, then the damper goes like this, just gets in. But if you push it hard, you see, like this, it stops. So that hard means that you are applying too much speed. So this is in fact C times x dot. And this is moving this way, M. So F equals MA. So let's write MA on this side. So I have M. A is in fact second derivative of this, x double dot. And this is in this way, so A is in this way, that's the positive. And those two are on the other side, so on negative forces, so minus kx minus cx dot. And there's no force applied. I'm assuming that it is simply, it's moving. So and I will tell you how you can move this thing, say. So let's put them together, and on one side mx double dot plus cx dot plus kx is 0. If I divide by m, I have c over m x dot plus k over m x. So this is equation of free vibration. Equation of free vibration. Free means that I'm not forcing anything, so there is no force, external force applied. As you can see, this is a second order linear differential equation with constant coefficients, and I'm assuming that m doesn't change, k and c also, they do not change. So all coefficients are constant. So, okay, so now this system, if you leave it like this, it never moves. This equation, it doesn't go away. The equation is there. So if I don't do anything, then the zero solution applies. Right? I'm not interested in zero solution. So if there is nothing happening to this system, the zero solution is there. It's not moving. So what happens when if it moves? So either I pull it like this. So if I pull it, I am giving it an initial x. Okay, so if I pull this thing to the right, or push it to the left, say, then I'm saying that. So if I say I pull this and then let it go, so it goes and vibrates, right? So that's in fact giving it an initial position. So let's say this is x0. Now, what is x prime or x dot? What is the other one? The other one is this. If I tap it like this, boom, boom, or this way, boom, boom, and I leave it. So if tap is impact, right? Impact produces speed. So if I tap it, I am giving it initial velocity, initial speed. So that is tap or something like that, say, and I will get x dot at 0 v0. I'm not saying both of them happen. You can both pull it and tap it, yeah, then you have both of them. But most often one of them happens. Most often either you pull it and let it go, or you tap it and let it go. So if I have these two, then I can solve this, and I will get, say, non-zero solution. Now, as you see, I have this is positive. Everything here is positive. M, C, and K are positive, and so I should, let me write down the solution for. Let me write down the r squared plus c over m r plus k over m. That's the characteristic equation. And the solution to this characteristic equation r is minus c over m plus minus square root of c over m squared minus 4ac, 4 k over m, right, divided by 2. So, when do we have vibration? So you can say, oh, you can have a situation like this. You just pull it and let it go. It just goes here and stops. Or you pull it and let it go, and it goes like this. Boom, 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 stops. Well, it stops because it has damper. Now, this equation, as we observe, well, I'm saying that either the first one happens or the second one. The third one, it's really improbable to happen, to get this thing exactly zero. That's just wow. So when do we have the second one? The second one is in fact vibration. We have sine and cosine. Vibration and oscillation comes from sine and cosine. So vibration happens if this is negative. If this is negative. If this is negative. So if I have C over M squared less than 4K over M. So vibration happens if this is less than this. Now, when does this usually happen? This happens when C is small, right? So if I put C, a huge C here, which means I have like a huge damper, damping just so tough. If this C is so large and makes this under this radical a positive number, then I have that situation. I pull it and let it go, and it goes like this, stops. So that's a huge damper. But if C is small enough, then it goes and comes back, vibrates until it stops. So we have to choose this C and K so that this happens, and if we do that, we will get vibration. Now, what does it look like? If that happens and I get vibrations, then let me draw the picture for you. You can write down the formula, but the formula is not what I'm interested in. So it starts somewhere here, say, and then goes like this. And dies. So if this happens to any situation, not just this vibration, it happens to any equation. When you solve an equation, the case 2 will give you something like this. If the middle term, if the b is not 0, if that b is not 0, so if I had this situation, e to power alpha t, for example, c1 cosine beta t plus c2 sine beta t, then this curve here is the thing that makes this damp is this. It comes from this b, it comes from the middle. Let me write this down again. X double dot plus c over m, x dot plus b over m, x 0. So it comes from this guy here. And it's minus. Remember, this alpha here is minus. So for this vibration, I have e to power minus c over m t. So it's dampened because this kills this thing. E1 minus ct is like this, goes down. So this thing, this in fact goes down like this. So that this is in fact like e to power alpha t, and alpha is less than that. And also you see that from the other side too. That's in fact minus e to power alpha t on the other side, minus. So it vibrates between these two curves. So you see that curve is between these two. And this, when alpha is less than 0, forces that to die down. So it goes down, dies down. Now, what are these two? What are these two? Physically saying. So, let me show you what they are. First of all, this is x0. That's where you start. X dot 0 is what? That's velocity or speed at the beginning. So at x dot, this one, slope of this is v0. So slope of this is V0. Now, depending on whether there's a positive or negative, it might start like the other way, or even might start here. If you, this is pulling, say this is pushing. If you push it, then it goes like this. So anyway, physically, those two, the x0 and x dot 0 are those two. The initial position, which is x0, and the initial, say, speed. Now, this is in fact the t-axis, and this is the x-axis in this situation. Okay, so that is interpretation in physical sense for this physics problem or mechanics problem, mechanical vibrations. Okay. Now, the same applies to just simple circuits in electronics, electrical engineering. If you ever take that circuits, if you are in that studying electrical engineering, you will see something very similar over there. Okay. So let me erase this and okay, now particular solution. Okay, I have Ly, which is this thing, equals some G of t. Okay. So I first solve this, 0, and this gives me a complementary solution. Then I solve this, and that gives me Y particular. And this Y particular is just one solution of this, which is one solution of Ly equals GT. Now let's compare with the situation that we had in linear algebra. Compare. When I had AX equals B, that's what we would do. We would solve this thing, and that would give me X of homogeneous. So that would give me the homogeneous solution, where let's call this complementary like the other one. Then I would solve this and find just one solution. Remember, we would just find one solution. And that one solution was the particular solution. And X in general was XC plus XP. Like here, Y will be YC plus Y. Okay, so it's basically the same problem, because remember that L is a linear function, in fact a linear operator. And this is also a matrix, so which gives me a linear transformation. So basically, we are doing the same thing. Theoretically, say we are doing the same thing. Now I discussed this one. You know how to find it. Now let's try to find yp when we have a function on the right side. This gt. Sometimes it's called the forcing function. Now, why is it forcing function? Because I will give you the example, the vibrations at the end, and you will see that if you apply some force, then you just go left and right because of that force, say, and that's called forced vibration. So when you have a force on this side, you have forced vibration, say, if that effect is modeling vibrations. Okay, so there are different ways of to find particular solution. If GT has certain form, then the easiest way to do it is using a method called the method of undetermined coefficients, yeah, undetermined. Method of undetermined coefficients. There is another method which I will discuss that is more general and applies to almost any GT. This one applies to certain GTs, and I will discuss just some of them. You can find in the book that like a table or something that discusses even different things. But I think it's let's just use this method for the simple functions. So I will have, this is in fact 3.5. 3.5 non-homogeneous equations. Method of undetermined coefficients. So here I have Ly equals GT. I will discuss three types. GT is a polynomial. 2, GT is an exponential function, e to power, say, gamma t, for example. And 3, GT is something like this, a cosine, say, so say gamma t plus b sine gamma t. Right. And 4 is a combination of these. A linear combination of 1, 2, and 3. Okay, so, well, this one, if I give you a linear combination of all these things in like an exam, for example, then it will take a long time. So basically, you shouldn't expect something like this. Or maybe it happens in practice. Maybe you have such a forcing function on the right side. But let's try each one of them because it's very easy when you solve for this and for this and for this. If you have a combination, then you solve for this separately, for this separately, for this separately, and then put them together. Okay, so, and I will tell you, I will come back to this number 4 again. So let me start with number 1. So 1 is when GT is a polynomial of degree, let's say something. Right. So we have Ly equals GT. So you have to, well, I'm not going to give that theorem, but there is a nice theorem that says, okay, if you have a polynomial, then GT, the particular solution, is also a polynomial. It's very easy to see that, you have an intuitive idea of why this happens. So if it's a polynomial, then y is also a polynomial of the same degree. So in this case, let the particular solution be a polynomial with unknown coefficients, polynomial with unknown coefficients, with undetermined coefficients. With the same degree as GT. So you just choose a polynomial with the same degree with undetermined coefficients. Then you just set them equal and find the coefficients. Now I will give you an example and you will see how easy it is. So if you have a polynomial of degree n, then the particular solution is a polynomial of degree n. Not the same, but with different coefficients. So let me erase this and give you an example. Well, let's write the one that we know, the complementary solution. That was example 1, I guess. Yeah, 5y prime plus 6y, and then write just a polynomial degree to say x. No, this is t. So we are dealing with t. So t squared plus 5t minus say 6. No, let's look like 5. Why am I always writing this? So let's say 4 minus 8. So, oh. So y particular should be the same as the same. Yeah, I guess this, you don't see that, so let me just use the black pen, black marker. So y particular should be similar. So it is a t squared plus b t plus c. So the a, b, and c to be determined. A, b, and c to be determined. Now, this yp satisfies the equation. We have yp double prime plus 5 y prime p 6yp is in fact the same. This should be the same. That is not equality. That is like an identity. So this should be the same as t squared for t minus 8. Which means whatever I get here, which is a polynomial, that polynomial should be exactly this. That's why I chose t squared, right? Because if I choose t to the power 3, then the coefficient of that should be 0. So I can just continue and go on up to t 10,000, and the coefficients of those will be 0 because of this last one, which you don't see anything more than t squared. You can check, you can just go and write, say, d t to the power 3 and see for yourself what happens. Okay, anyway, so I need this one and this one. So let me just find y prime. So y prime is 5 times y prime is 2at plus b. So y double prime will be simply 2a, right? So y double prime is 2a, and y prime is this, plus 6 times at squared plus bt plus c, and this should be the same as the right hand side, which is t squared plus 4t minus 8. Okay? So let me double check. Y prime is 2at plus b, and y double prime is 2a. So this is y double prime, y prime, and y. And that should be the same as t squared minus 4t minus 8. So let me erase this and continue here. Okay. Let's put this together. I have 6a t squared. Then t, what do I have for t? I have 5 times this 2, 10a. It has t here, and this one has t, so plus 6b times t. And constants, I have a constant here, 2a, and a constant here, 5b, plus 6c. And this should be the same as t squared, plus 4t minus 8. Okay? Let me double check. 6at squared I have here, 10at and 6b here, 2a, 5b, 6c. Okay. So the coefficients on the two sides should be this should be the same as that, exactly. So I have this being exactly the same is 1, then 10a plus 6b should be 4, and the last one 2a plus 5b plus 6c should be minus 8. So let me erase this and find a, b, and c. Now this, this method will usually gives you a immediately. If you have chosen correctly, then from the first one you get a. A is 1, 6. Now I have a here, find b. So this one gives me 6. B is 4 minus 10, 1 over 6. 10 times 1 over 6, so that is 4 minus, what's that? So that's 5 thirds. 5 over 3, 12 minus 5. That's it. So from here I have 6c. So 6c will be minus 8 minus 2a, 2 times 1 over 6, minus 5b, 7 thirds. So I have minus 8 minus 1 thirds minus 35 over 3. Okay. So it's minus something. 3, 24 plus 1 plus 35. That's 25, 35, that is 60, isn't it? I guess it's minus 35, 60 over 3, which is minus 20. So the particular solution in our situation is, what was it, 1/6 y squared, t squared, sorry, 1/6 t squared plus 7 30 minus 20. Now I found the particular, the complementary solution. That was example number 1. So y is in fact y complementary plus y particular. Remember, the complementary solution was something like this: c1 e to power minus 2t plus c2 e to power minus 3t, and the particular solution is added to this, and that is my general solution. Why general? Because I have c1, c2 plus 1/6 t squared plus 7 thirds t minus 20. Okay. So again, I checked my calculations here, as I'm just writing it down without any notes. So I might have made mistakes, which I usually make mistakes. So please check and correct my mistakes. Anyway, so that was a solution, complete solution for a differential equation like that, which you can, if you use any say like Mathematica, for example, or Wolfram Alpha, it probably will give you something similar to this. It might say C1, C2, it's written differently, but you can also check Wolfram for this one. Now, I will discuss a problem like this when initial conditions are given. Because if initial conditions are given, you have to find, you have to use this for initial condition, not the complementary one. You have to use this one for initial condition. Which makes problem a little harder, because then you have to find the derivative of this thing and then plug in, if it's at 0, then plug in 0. But anyway, you have to use this to find C1, C2, not the complementary solution. When you are dealing with forced vibration with initial conditions, or forced and we have GT and also initial conditions. Okay, so let me stop and I will give you examples of the other two cases. Okay, so see you next time.